Supervised machine learning algorithms. Supervised learning is a popular category of machine learning algorithms that involves training models using labeled data. In supervised learning, the algorithm learns to map input data to corresponding output labels based on the provided examples. These algorithms are widely used for tasks such as classification, regression, and prediction. In this article, we will discuss the main concepts, types, and applications of supervised learning algorithms. 1. Supervised learning basics. Supervised learning involves a training phase where the algorithm learns from labeled data and a prediction phase where it applies the learned knowledge to make predictions on unseen data. The labeled data consists of input features, also called independent variables, and their corresponding output labels, also called dependent variables or targets. 2. Classification algorithms. Classification algorithms aim to categorize input data into predefined classes or categories. They learn from labeled examples to build a model that can assign correct class labels to new, unseen data points. Some common classification algorithms include A. Logistic regression. This algorithm models the relationship between the input features and the probability of belonging to different classes. It uses a logistic function to map the input to a probability distribution over the classes. B. Decision trees. Decision trees are hierarchical structures that make sequential decisions based on feature values to assign class labels. They divide the feature space into smaller regions and associate a class label with each region. Circa support vector machines, SVM. SVM constructs a hyperplane or set of hyperplanes to separate different classes. It aims to maximize the margin between the classes, effectively finding the best decision boundary. D. Random forest. Random forest combines multiple decision trees to form an ensemble model. Each tree is trained on a different subset of the data, and the final prediction is made by majority voting or averaging the predictions of individual trees. E. Naive Bayes. Naive Bayes is based on Bayes' theorem and assumes independence between features. It calculates the probability of each class given the input features and assigns the class with the highest probability. 3. Regression algorithms. Regression algorithms are used when the output variable is continuous, and the goal is to predict a numeric value. These algorithms learn from labeled examples to establish a relationship between the input features and the output variable. Some common regression algorithms include A. Linear regression. Linear regression models the relationship between input features and the output variable as a linear function. It finds the best fit line that minimizes the difference between predicted and actual values. B. Polynomial regression. Polynomial regression extends linear regression by incorporating polynomial terms of input features. It can capture nonlinear relationships between the features and the output variable. Circa support vector regression, SVR. SVR applies the principles of SVM to regression problems. It finds a hyperplane that has a maximum number of data points within a certain distance, called the epsilon tube. D. Decision tree regression. Similar to decision trees for classification, decision tree regression makes predictions by dividing the feature space into smaller regions and associating a numerical value with each region. E. Random forest regression. Random forest regression applies the ensemble technique of random forest to regression problems. It combines multiple decision trees to make predictions on continuous variables. 4. Model evaluation. To assess the performance of supervised learning algorithms, various evaluation metrics are used. Common metrics for classification include accuracy, precision, recall, F1 score, and area under the receiver operating characteristic, ROC, curve. For regression, metrics like mean squared error, MSE, mean absolute error, MAE, and R-squared are commonly used. 5. Applications of supervised learning. Supervised learning algorithms find applications in various domains, including A. Spam email classification. Classification algorithms can be used to identify and filter out spam emails from legitimate ones. B. Disease diagnosis. Classification models can assist doctors in diagnosing diseases based on symptoms and medical test results. Circa sentiment analysis. Classification algorithms can analyze text data to determine the sentiment, positive, negative, or neutral, expressed in customer reviews or social media posts. D. Stock market prediction. Regression algorithms can be used to predict stock prices based on historical data and market trends. E. Image recognition. Classification algorithms can classify images into different categories, such as identifying objects or recognizing facial expressions. F. Credit scoring. Classification algorithms can assess the creditworthiness of individuals based on their financial history and other relevant factors. G. Autonomous driving. Supervised learning algorithms can be used in self-driving cars to classify objects on the road, such as pedestrians, vehicles, and traffic signs. H. Natural language processing. Supervised learning algorithms play a vital role in tasks like language translation, named entity recognition, and text summarization. 6. Challenges and considerations. While supervised learning algorithms are powerful tools, they also have certain challenges and considerations. A. Data quality. The quality and representativeness of the labeled data used for training directly impact the accuracy and performance of the models. B. Overfitting and underfitting. Overfitting occurs when a model performs well on the training data but fails to generalize to new, unseen data. Underfitting, on the other hand, occurs when the model is too simple and fails to capture the underlying patterns in the data. Circa feature selection. Choosing the relevant features that have the most impact on the output is crucial for model performance. Irrelevant or redundant features can introduce noise and degrade the accuracy. D. Bias and fairness. Supervised learning algorithms can inherit biases present in the labeled data. It is important to ensure fairness and mitigate biases to avoid discriminatory outcomes. E. Scalability. Some supervised learning algorithms may not scale well to large datasets or high-dimensional feature spaces. Efficient algorithms and computational resources are required for handling such scenarios. 7. Future trends. Supervised learning continues to evolve with advancements in technology. Some future trends include: A. Deep learning. Deep learning, a subset of machine learning, focuses on neural networks with multiple layers. It has shown remarkable success in various applications, such as image recognition and natural language processing. B. Transfer learning. Transfer learning aims to transfer knowledge learned from one task to another related task, reducing the need for extensive labeled data. Circa explainable AI. As the complexity of models increases, there is a growing need for interpretability and transparency in AI systems. Research is ongoing to develop methods for explaining the decisions made by supervised learning models. D. Federated learning. Federated learning allows models to be trained on distributed data sources while preserving privacy. This approach is particularly useful in scenarios where data cannot be shared centrally. 8. Ensemble methods. Ensemble methods combine multiple supervised learning algorithms to improve prediction accuracy and generalization. These methods harness the wisdom of multiple models by aggregating their predictions. Popular ensemble methods include: A. Bagging. Bagging, bootstrap aggregating, involves training multiple models on bootstrap samples of the training data and combining their predictions through majority voting or averaging. B. Boosting. Boosting algorithms build models sequentially, where each subsequent model focuses on the examples that were misclassified by previous models. This iterative process improves the overall performance of the ensemble. Circa stacking. Stacking combines multiple models by training a meta-model that learns how to weigh the predictions of the individual models. The meta-model takes the outputs of the base models as input and generates the final prediction. D. AdaBoost. AdaBoost, adaptive boosting, assigns higher weights to misclassified examples, guiding subsequent models to focus on them. The final prediction is made by aggregating the predictions of all models, weighted by their performance. 9. Handling imbalanced data. In many real-world scenarios, the labeled data may be imbalanced, meaning that the number of examples in one class significantly outweighs the others. Supervised learning algorithms can be sensitive to such imbalances, leading to biased predictions. To address this, techniques like oversampling the minority class, undersampling the majority class, or using algorithms specifically designed for imbalanced data, e.g., SMOT, can be employed. 10. Hyperparameter tuning. Supervised learning algorithms often contain hyperparameters, which are parameters that are not learned from the data but set before training. Proper tuning of these hyperparameters is crucial for achieving optimal model performance. Techniques like grid search, random search, or more advanced optimization methods, e.g., Bayesian optimization, can be used to find the best combination of hyperparameters. 11. Continual learning and online learning. Supervised learning algorithms are typically trained on fixed datasets offline. However, in some scenarios, new data continuously arrives, requiring models to adapt and learn from the incoming information. Continual learning and online learning techniques enable models to incrementally update their knowledge as new data becomes available, ensuring the model remains up-to-date and relevant. 12. Supervised learning libraries and frameworks. To facilitate the implementation and usage of supervised learning algorithms, there are various libraries and frameworks available. Popular ones include scikit-learn for Python, TensorFlow, Keras, PyTorch, and Microsoft Cognitive Toolkit, CNTK. These libraries provide a wide range of pre-implemented algorithms, tools for data preprocessing, and evaluation metrics. 13. Ethical considerations. While using supervised learning algorithms, ethical considerations must be taken into account. Biases present in the labeled data can lead to biased predictions and discriminatory outcomes. It is important to ensure fairness, transparency, and accountability throughout the entire life cycle of the algorithm, from data collection to deployment. 14. Collaborative and federated learning. Collaborative learning and federated learning approaches aim to leverage the collective knowledge from multiple parties while respecting data privacy. Collaborative learning involves training models collaboratively using combined datasets, whereas federated learning allows models to be trained on decentralized data sources without sharing raw data, thereby maintaining data privacy. 15. Human-in-the-loop supervised learning. Human-in-the-loop approaches combine the power of machine learning algorithms with human expertise. These methods involve iterative cycles of model training, human feedback, and model updates. Humans provide insights, correct errors, and validate the outputs, making the learning process more accurate and reliable. In summary, supervised learning algorithms form a fundamental branch of machine learning, where models are trained on labeled data to make predictions and classifications. They offer a wide range of applications, from classification and regression to image recognition and sentiment. Thanks for watching.